Okay, let us study chapter 17, Lorentz invariance and 4 vectors. 17.1, 4 vectors. Okay. Four vectors means that it is a vector composed of 4 components, but it is different from Euclidean 4 vector. It is defined in the Minkowski space. Minkowski space is the space whose simple definition of 4 vector is, let us begin with the event. This is the event for a particle moving with velocity v in space. Okay. In another frame of reference where the particle is at rest, that means we are considering a particle that is moving with constant velocity, and if we put the origin at the particle, then the event is just like that. They are the same events but seen at different frame of reference. We call these events to be 4 vectors. And the basic relationship is, according to our previous derivation, that is just time dilation relationship. If I divide both sides by c squared and factor the left hand side with t squared, and take the square root and take only positive root, this is time dilation relationship. Even though time dilates, square of time subtracted by spatial part squared is always conserved. It's possible to have the particle have larger velocity, in that case, we have another gamma factor, but that cancels when I square this and subtract this one by squared value. Okay, so we define x mu to be c t v t. This is for the special case where the particle is moving with a constant velocity v, but we can replace it by the spatial position of the particle. Okay. We have a special notation that the subscript, a Greek subscript mu, is attached on top of the right side as an upper index. So we call this one to be a 4 vector. So this is another name is displacement 4 displacement. And as we have seen that the square of the first component, that is time component, subtracted by the square of the spatial component, is defined to be the square of this 4 vector. And we use notation x squared. This is not indicating the second component. It is just the square of this 4 vector is CT is defined to be x0, and x spatial component of the x vector can be written as x1, x2, and x3. So this is composed of 4 components. X squared is 0th component squared subtracted by first, second, and third. Or simply we rewrite Now we define 2 ways of writing 4 vectors. This is called contravariant form, and this guy is called covariant form. And the 0th component here we can find that x0 subscript and xi equals minus xi, right? The reason why we use this strange notation for putting one index as an upper index and one index as a lower index is to simplify the squaring of 2 vectors. X squared was x0 squared subtracted by x1 squared, x2 squared, x3 squared, and this can be written as x0, x0, because upper index and lower index is the same for the 0th component, and this one can be written as minus x1 times x1 equals, put one's upper index, and this is x1 in lower index. In the same way, so we can write it as x mu, x mu. Sure, we need to put the summation notation for I runs from 0 to 3, but we will use Einstein's notation, then we ignore this. Just write it x mu, then it indicates that it is summed over the Greek index mu that is over 0 to 3. Okay? So, as a summary, what is 4 vector? We don't know exactly yet. First of all, 4 displacement that indicates the time and space of a particle's event. And that is called a 4 vector. Is a kind of 4 vector. And the spatial characteristic of this 4 vector, this 4 displacement 4 vector, was this value was invariant. Invariant under Lorentz transformation. So we would like to define a 4 vector like that. four displacement is a four vector, and this guy has a special condition that it's a square. It's a square is invariant on the Lorentz transformation. Our generalized four vector definition is y mu is composed of y0, y1, y2, and y3, and I don't know whether this y is displacement or not. Let's assume if this guy is a four vector, then this guy is invariant. And each component of this four vector transforms on boost or rotation. It transforms. The transform respects the Lorentz transformation. So we call square of this four vector is invariant, and each component of this four vector is covariant. Okay, each component of this four vector change its own component depending on the reference frame, but the rule is governed by the Lorentz transformation. Okay, so we would like to construct more four vectors from this fundamental four vector, that is a four displacement. So in this chapter, we will extend this idea to define four velocity and four momentum. Okay, now let us define metric tensor. When we square four displacement, our first way of writing was x mu, x mu. Because these are numbers, we can, they commute. So it is possible to write like that. But let us recall this case. 3 vector squared. It is xi, xi. Where I runs from 1 to 3. But we remember, this is xi, delta ij, xj. They are the same. Because it can be understood as x1, x2, x3, 1, 1, 1, 0, 0, 0, 0, 0, 0, x1, x2, and x3 to make it x1 squared, x2 squared, and x3 squared, right? We'd like here this Kronecker delta is a metric tensor. Metric tensor is a matrix that is sandwiched by two vectors to make this product to be the length squared. Okay. In the case of a Euclidean vector, this is really a length squared. But this kind of four vector squared is not really the same as the physical length, right? Because this is a time, sure it is length, time multiplied by speed of light, and this has a length dimension, spatial vector. Now we define a generalized length in 4 dimension, that is called the Minkowski space. X squared to be like that. Then why don't we copy this method? X mu and put different Greek letter x nu. And what is the matrix between that? We can write explicitly like this: x0, x1, x2, x3, and there is a matrix x0, x1, x2, x3. Okay? What is the answer? This matrix must be 1, minus 1, minus 1, minus 1. Okay? If they are both up, it is 1, minus 1, minus 1, minus 1, and there is no crossing term. Okay? So we call this one to be G. So I'd like to put Greek letter for the repeated indices. So there should be some mu here and nu here. However, what happens if I write like that? It's the same, but our convention is when I square when I square a full vector, one index must be up, the other index must be down, because I have to take into account the sign difference for the time part and the spatial part. That is, the sign difference appears due to the difference between up and down. If we make use of x mu mu, then what happens? This sign becomes plus. So this kind of expression is wrong. So our convention is to use repeated indices, one up and the other down. So this is not good expression. So we use mu as a lower index and nu as a lower index. So mu mu and nu nu, that connect. So this matrix, this is x mu, this is g mu nu, and this is x nu. Okay. What happens if I make use of x mu, x nu? Then they will become minus, 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 right? In order to have the same answer, or the squared value, our g mu nu, because this mu is down, this mu must up, up, down. So this g mu nu is the same as this g mu nu. So numerical value for these two matrices are the same. However, in order to make the expression consistent, we just use lower index for this kind of expression. Okay? So this G is metric tensor. All right. Let us review the Euclidean rotation. Rotation in the Euclidean space before we go ahead with the properties of Lorentz transformation matrix. Let us consider a vector x, which is a Euclidean vector. And I'd like to transform this one to another frame. And if it is a column vector, something like that, then in the prime system, there must be some matrix, 3 by 3 matrix. So let us call this matrix as R. If I make use of components, ith component is Rij Xj, right? In the Minkowski space, 4-vector squared is conserved. In the Euclidean space, under rotation, length of a vector conserves. So, to make it simple, we just make use of length squared, and that means x prime squared is equal to x squared. We would like to simplify, interpret this relationship by making use of rotation matrix R. So, xi prime, if I want to square this, x prime I equals x prime k x k x k, where I is summed and k is summed. So let us make use of this expression. Then this guy is Rij Xj. Because j is a dummy index, when I use this, I have to use different dummy index. But this is I fixed. I k x k. All right. So these are numbers. They commute. If I write this expression as a product of matrices, I cannot commute them. But because they are numbers, okay? What is the right side? I have xj, xk. So if I want to express this one as a product of xj, xk, I have to multiply delta jk. Then this and this are the same. This relation must be true for any vector x. That means this over vector is the same always for any component. So Rij Rik equals delta jk. Actually, this is transpose ji and rik equals delta jk is identity matrix, jk component of the jk matrix. If I combine this, because these two indices are connected, this is just a product R transpose and R, jk equals identity jk. This is true for any j and k that gives R transpose R equals identity. In a similar way, we can prove that R transpose is identity too. It's your homework. I'd like to copy this to find the relationship for the Lorentz transformation. I have a condition that now we are considering 4-vector. Our 4-vector x prime mu is one frame, another frame. That is connected by a Lorentz transformation matrix. What? Mu and nu. Okay. This is matrix, so these two indices must be the same. Okay? If I follow the Lorentz covariant way of writing, this can also be written lambda, mu, nu, then x, nu. However, the reason why I write like that is if we remember. Right? These two are expressed as x prime 0, x prime 1. This is x prime, x unprime 0, x 1, something like that. So, left hand side, each part of x, left hand side is expressed as mu up. Right hand side, x is a nu up. And this matrix must have the up part, and this is the sum. That must be the lower index. So, here, prime. So, even though I write this, I do not use this. And let us use a similar relationship. X prime squared is equal to x squared. Okay? X prime squared is x prime mu g mu nu x prime nu. Okay? That is what? Lambda mu. Because mu nu are already used, let me use mu alpha x alpha g mu nu and lambda nu beta. You don't have to put a dotted line later, but I'm using this in order not to make you confused. X beta. Okay? So I have mu alpha again. Again, they commute because they are all numbers. All right. Because at the end of the day, we have to find this expression x alpha, g alpha beta, x beta for any x, for any 4 vector x. Our condition is that this guy is the same as this guy. Exactly. So this is the relation that is equivalent to this part. Why? Let us make use of g mu nu here. Then this nu goes down and beta. If I make a transpose of this matrix, like this transpose, transpose is change of 2 indices. But covariance of this mu, this, if it is up, then this should be up forever. Because it is up and it meets down, and this guy will go away, and this is a product whose indices for alpha and beta are all down. Okay? So lambda transpose lambda is the same as G. Okay? But if you may be unhappy with the structure of this lambda and this lambda. If I shift this variable down, then the matrix shape becomes different. No, if I change one up and down, then these guys change its sign. So this is our first trial. However, it's better to put G mu nu here. Lambda transpose alpha mu and nu beta G mu nu. Then it can be written as lambda transpose G lambda alpha beta. Perhaps this expression will be better. Where's my book? All right. Okay. This is the relationship for the four displacement. But what happens to the 4 vector? Because 4 vector is the same as the displacement as far as the Lorentz transformation is concerned. Whether this is x or not, for example, I want to define scalar product A dot B to be A mu G mu nu B nu, where A and B are 4 vector. We don't know what they are, but let's assume they are 4 vectors. So 4 vector, each component of 4 vector follows the Lorentz transformation, and its own square is invariant on the Lorentz transformation. And let us see what happens, how this scalar product A dot B transform on the Lorentz transformation. It is non-trivial because until now we used just the square of a single matrix, a single 4 vector, but it is just simple. If I want to consider A dot B in the unprimed system and prime system, what's different? A prime dot B prime equals this. And this is A, and this is B. This is A, B, and this is AB. But we have shown that this guy is the same as this already. So this is A dot B. Although we have shown that square of a 4 vector is conserved, actually 4 displacement squared is invariant on the Lorentz transformation. However, it is true for the scalar product between any 2 4 vectors. So this is a very powerful condition. For velocity,
방금 풀었다.